Spectrometry, nuclear resonance. Any spinning charged particle will resonate with a magnetic field. In this case, we'll look at the nucleus and look at nuclear magnetic resonance, or NMR. Nuclei are composed of fermions. Protons have a mass of 1 atomic mass unit and a charge of +1, as you know. Neutrons have a mass of approximately 1 atomic mass unit and a charge of 0. Therefore, the nucleus has a total spin, which is called I. The spin dynamics of a nucleus are complicated. Simply adding the spins of each nuclei do not work for heavier elements, but work quite well for lighter elements. However, the total spin, I, is still quantized, with m sub I being allowed any integer value between +I and -I. Since the nucleus is a spinning charge, it also has a magnetic moment. However, because the nucleus is much larger than an electron, the magnetic moment is smaller. It is dispersed over a larger volume. For an electron, the magnetic moment is the Bohr magnetron, 9.274 times 10 to the -24th ampere meter squared. For a nucleus, you have the nuclear magnetron, 9.66 times 10 to the -27th ampere meter squared, a factor of 1,000 smaller. We will begin this overview by looking at hydrogen NMR. A hydrogen 1, as you know, is simply a proton. It has a dimensionless G value of 5.5857, and therefore its precession frequency, as with any charged particle, is the G value times the magneton times the applied field divided by h. In a 1.5 Tesla field, we have 5.857 G times 9.66 times 10 to the -27th ampere meter squared for the nuclear magneton in 1.5 Tesla divided by Planck's constant 6.626 times 10 to the -34th joule seconds, giving a precession frequency of 1.22 times 10 to the 8th hertz, or 122.18 megahertz. Therefore, protons resonate in the radio frequency. At any given field strength, the natural precession frequency of a proton is called the Larmor frequency, or mu sub L. Nuclear magnetic resonance is more complicated than electron resonance due to something called shielding. NMR is also performed under an external magnetic field, just as EPR is. However, protons are surrounded by electrons. Electrons are also spinning charged particles. Therefore, they have a magnetic field and they absorb part of the external magnetic field. Shielding produces a lower effective field felt by the proton, symbolized by B subscript effective, EFF. Protons attached to an electron withdrawing group are less shielded. They feel a stronger effective magnetic field, therefore they spin at a relatively higher frequency. They are said to be downfield. Protons attached to an electron donating group are more shielding. They feel a weaker effective magnetic field. They therefore spin at a relatively lower frequency and are said to be upfield. The proton NMR scale is called the delta scale. This is a relative scale. Protons don't resonate in the megahertz range. However, shielding only changes the frequency by a factor of several hertz. The delta scale is therefore calculated in parts per million, ppm. In other words, in frequency, one change in hertz of the resonance frequency per million hertz of resonance. Since the scale is relative, a reference is needed to measure against. The compound tetramethylsilane, or TMS, is usually used depending on solubility. The formula of TMS is SiCH3 4 times. A tetrahedral silicon surrounded by 4 methyl groups. This is a unique compound because hydrogen is more electronegative than carbon, and carbon is more electronegative than silicon. Therefore, hydrogen is the most electronegative element in TMS. This is the most shielded a proton can possibly be, and TMS is set as the reference at 0 ppm. Remaining with proton NMR, we will now look at how we calculate delta, which is also called the chemical shift. Again, any spinning particle will resonate at charged particle will resonate at a frequency equal to g times the nuclear magnetron times the applied field divided by Planck's constant. The chemical shift is calculated as follows. In any given compound, you will see in a while, various protons will resonate at various frequencies. This is the frequency of the sample, relative to the frequency of the reference, divided by the natural precession frequency or the Larmor frequency, and you get an answer in the range of 10 to the minus 6 hertz. In other words, 1 part per million. To simplify this, the shielding constant alpha can be easily calculated because, as can be seen, the precession frequency is related to the applied field B. Essentially, sigma is the frequency of the sample as a fraction of the Larmor frequency. The effective field then is some percentage of the applied field, or 1 minus sigma times B. Each unique hydrogen in a sample has its own sigma. So therefore, the frequency of the sample minus the frequency of the reference over the Larmor frequency, the part per million scale, is equal to sigma of the reference minus sigma, the shielding constant of the sample, divided by 1 minus sigma of the sample. The effect of shielding on an NMR can be seen by looking at the proton NMR of ethanol, C2H5OH, or as shown, a CH3, a CH2, and an OH group. First, one must identify magnetically equivalent protons. This means rank the protons relative to their position to the most electron withdrawing group, in this case the OH. You see there are 2 protons B closest to the oxygen and 3 protons A farther away. The H on the OH, C star, is generally not seen on an NMR as alcoholic and acidic protons are exchangeable. We now look at a simple spectrum. With the reference peak set at 0, the most shielded peak, A, will appear downfield since it is furthest from the oxygen. The next most shielded peak from protons B will appear next, and if seen, the most deshielded peak, C, will appear upfield. Note, NMR is actually quantitative. The ratio of the peak areas, 3 to 2 to 1, is the same as the ratio between hydrogen A, hydrogen B, and hydrogen C. The area under any given peak is related to the amount of signal and therefore the number of protons contributing to that peak. As mentioned, the local magnetic area of a proton is complicated. Protons are surrounded by electrons. The amount of electron density gives rise to the chemical shift. Additionally, protons are next to other protons on adjacent carbons. Each proton is a spinning charge with a spin of I of 1/2. M sub I can be either pointed up, plus 1/2, or minus 1/2. Each combination gives a different magnetic field. So let's look at the last fraction of ethanol, the CH2CH3, with the A protons being on CH3, the B protons on CH2. For any given A proton, that is next to 2 B protons. Their spins can be arranged either up and up, down and up and down, or down and down. You notice the middle two, down up and up down, are degenerate. Therefore, HA will be split by hydrogen B into 3 peaks, a triplet. The ratio of each of those peaks will be 1 combination for straight up, 2 combinations for up and down, 1 for straight down, or 1 to 2 to 1. The situation faced by hydrogen B, being next to 3 hydrogen A's, is even more complex. Those 3 hydrogens in any given time could all be spinning up. There are 3 ways they could be spinning 1 down and 2 up that are degenerate. There are also 3 ways they could be spinning 1 up and 2 down that are energetically degenerate. Or they could all be spinning down. Therefore, hydrogen B will be split by hydrogen A into a quartet of 3 peaks. Again, the ratio is equal to the number of possibilities that exist. The ratio between those 4 peaks will be 1 to 3 to 3 to 1. So let us return to the simple proton NMR of ethanol, CH3, CH2OH, and identify the splitting interactions. As the NMR is taken, the reference peak is still set to 0. However, the most shielded peak, the furthest downfield A, the furthest from the oxygen, is next to 2 B protons. Therefore, it will be split into a triplet by those 2 B protons. Next upfield, the next least shielded proton B is sitting next to a CH3 group with 3 A protons. Therefore, B is split into a quartet by the 3 A protons. The most deshielded proton C, again if it appears, has no neighbors, and therefore it is not split. It is interesting to note the total peak area is still 3 to 2 to 1, which is the ratio of hydrogen A to hydrogen B to hydrogen C. The total area under the peak remains unchanged after the split and is now divided into 2 or more subpeaks. For large molecules, the magnetic environment for a proton is even more complicated because interactions can exist through space. This is called the nuclear Overhauser effect. Large molecules, such as biomolecules, most famously DNA with its double helix, have various and changing conformations. Therefore, groups that may be widely separated from each other in the carbon-carbon backbone of the molecule can be near to each other in space. These groups will influence each other magnetically. Two-dimensional NMR, 2D NMR, is used to investigate these relationships. If you remember how resonance spectrometry works, a reference pulse aligns the spins. This reference pulse is propagated along the z-axis. A signal pulse then knocks down the spins. There are two axes left. That signal can either be propagated along the x or the y-axis. In 2D NMR, the x and y axes are pulsed sequentially. The signals from both are compared to determine through space relationships. A two-dimensional NMR utilizing the nuclear Overhauser effect is plotted in a box. Two spectra appear on the x-axis and the y-axis of the box. As you see, they are identical in composition and spacing, but are mirror images of each other. The molecule under investigation has four functional groups. Group 1 is highly shielded and is a triplet, meaning there are two adjacent hydrogens. Slightly less shielded, Group 2 is a singlet, meaning there are no hydrogens adjacent to it. Group 3, further upfield, is a quartet, meaning there are three adjacent hydrogens. And Group 4, the most deshielded, is a doublet, indicating two adjacent hydrogens. The signals from the two NMRs, one taken from the x direction and one from the y direction, interfere with each other. Along a diagonal, identical groups appear. 1 crosses with 1, 2 with 2, 3 with 3, and 4 with 4. However, the off-diagonal groups are the ones that are interacting through space. As you can see, this graph is symmetric. Group 1 intersects with Group 3 on both the upper and lower half. Therefore, those groups are near each other in space. Group 2 also interacts with Group 3, and Group 2 is also near Group 4, with, again, symmetric crossings in space. The intensity of these interference patterns is related to how far away or how close the two groups are to each other as the molecule goes through various conformations. Proton NMR is a very powerful analytical tool. There are several variables, all of which provide information about the molecule. First of all, the field strength, the only variable in the precession frequency. Stronger magnets will not change the ppm scale, since the ppm scale is relative and also relative to the precession frequency, which is related to the magnet. However, stronger magnets do increase sensitivity. The precession frequency, again, is equal to G times the nuclear magneton times the applied field strength divided by H. Everything in there is a constant except for the applied field strength. At 1.5 Tesla, a proton has a Larmor frequency of 122.1 megahertz. Therefore, a 1 part per million difference in spacing gives a resolution of 122 hertz. A larger magnet at 7.5 Tesla will give a Larmor frequency of 610.9 megahertz, and a 1 ppm difference is now 611 hertz, or approximately 5 times more sensitive. That sensitivity can be used to determine, first of all, what functional groups are present through the shielding. The shielding determines the relative ppm position of each group in a molecule, and different groups have characteristic positions, so one can look on tables to find out what is resonating where. The magnetic field is then affected by splitting, the effect that neighboring protons have on a proton. This gives an indication of what order these functional groups appear in a chain, because only direct neighbors can cause splitting. So now we know what the molecule is made of and where the pieces are. Finally, two-dimensional NMR can tell the investigator how that molecule is shaped, what conformations it is undergoing, and what changes it makes. Proton NMR is the most common type of NMR and the most intricate. However, nuclear resonance can also occur with other nuclei. Any nucleus with a half-integer spin I will resonate. Each nucleus has a different G value, and this G value changes the precession frequency. At 1.5 Tesla, a proton has a G of 5.5857 and precesses at 122 megahertz. Carbon-13 has a G value of only 1.4046 and precesses at 30.7 megahertz. Phosphorus, with G equal to 2.2634, precesses at 49.5 megahertz. Since essentially an NMR is nothing but a magnet with a radio transmitter attached, the NMR has to be retuned for any different element that one is looking for. Another difference between other magnetic resonances and that of a proton is that protons are the only atoms where you use an internal reference. For other nuclei, the absolute position of the peak indicates the local environment. For example, for carbon-13, the next most common type of NMR, positions indicate the type of carbon one is looking at: aliphatic, aromatic, sp3, sp2, sp1 hybridized. For other elements, including metals, the position indicates the coordination environment. If it happens to be sitting in an octahedral site, a tetrahedral site, a dodecahedral site, and a lattice, and so on. Additionally, since there are no neighbors along the backbone of a carbon molecule or in a crystal, no splitting is found when investigating the NMR of other nuclei.